Now that we've seen what the trapezoidal rule and Simpson's rule can do for us in terms of approximating a definite integral, we want to look at, well, how good of an approximation do we need? And if we know how good the approximation is that we are searching for, how many subintervals should we cut our interval up into so that our approximation by Simpson's rule or the trapezoidal rule will give me a good enough approximation for what I need it for? Well, to do that, we are going to look at the error that occurs when we use the trapezoidal rule and also the error that occurs when we use Simpson's rule to approximate a definite integral. So if I'm looking at approximating a definite integral using the trapezoidal rule specifically, if my function that's the integrand of the definite integral has continuous second derivative on that closed interval. So if I take this function, I take the first derivative, I differentiate it to get the second derivative, and I look at the domain of that second derivative. If that domain of that second derivative shows that it's continuous over the interval from a to b of my integration, on that closed interval, then the error in approximating this definite integral using the trapezoidal rule is that my error is going to be less than or equal to b minus a to the third power divided by 12n squared times, so that value, times the maximum that the absolute value of my second derivative of this function attains on that interval. So remember, we had the extreme value theorem of a function back when we were first looking at applications of derivatives. And that said that if you have a continuous function on a closed interval, you are guaranteed that that function attains an absolute max and an absolute min on the interval. Apply that extreme value theorem to the second derivative of this. Look at what the absolute max, absolute min are. Look at the absolute value of the max, the absolute value of the min, and take the biggest of those two numbers for this numerical value. So this is just representing a number, and it's representing the number that is the furthest distance the second derivative is away from the x-axis. Now, when I have a particular accuracy that I need to meet, I'm going to have this expression less than or equal to what it is that I need to meet as my accuracy, because if my error is less than this, and this is less than the accuracy that I'm going for, then my error will be less than that accuracy. So we want to remember that part of it. Now for Simpson's rule, my function has to have a continuous fourth derivative. So I would need to take this function, differentiate it once for the first derivative, another time for the second, another time for the third, another time for the fourth derivative. And then the error from Simpson's rule is b minus a to the fifth power divided by 180n to the fourth times the maximum of the absolute value of the fourth derivative on that interval. That's where I would use my extreme value theorem. Now certainly if you see that the function is always increasing or always decreasing over your interval, then you would be able to find out the maximum the absolute value has from the endpoints. But if it has anything where it has the mins and maxes for critical values in the interval, you need to check those out. So here are our examples. I've rewritten up what the trapezoidal rule error is and Simpson's rule error. And then for our question, we want to find n, the minimum number of subintervals needed, so how many n we would have to approximate the definite integral from 1 to 4 of 1 over 30 x to the 6th dx with an error of absolute value less than 0.00001 for trapezoidal and for Simpson's rule. So we're going to do it for both situations. Now, I know that we could find the exact value of this definite integral using the fundamental theorem of calculus. Through some work, we could even find it using our limit definition with our definite integral. But I want to use this particular example as just showing you how you would have to go through the calculations, and then you would just carry out the same process with your other continuous function that you may have. So first, trapezoidal rule. With this, we need to take our work with the trapezoidal rule, and we need to set that less than what the error is that they're imposing upon us, restrictions are. And we want to recall our values. Remember here, our A is the lower limit of integration, B is the upper limit of integration, our function f of x is the integrand, so that's 1 over 30 x to the 6th. And then n is what we're searching for, so we leave that n when we're doing the work. And then we have our maximum value of the absolute value of the second derivative of the function over that interval for the trapezoidal. So we're going to take our first derivative f prime of x, well, constant times letter base x to the power 6. We bring down the exponent, multiply it to the coefficient that's in front of it, keep the base, and subtract 1 for the exponent for the derivative. So that will be 6 over 30, or 1/5 x to the 5th. And then the second derivative, differentiate again. 5 times 1/5 is 1, x to the subtract 1 from 5, power of 4. So that's my second derivative. So now when you think about x to the 4th over the interval from 1 to 4, well, x to the 4th over the interval from 1 to 4, that is always increasing over that interval, and it's positive in increasing over that interval. The greatest value, the absolute value, is going to have on that interval is when it's at its right endpoint for this particular second derivative. So for this, our maximum value that the absolute value of the second derivative of the function is going to attain, well, that's going to be the value of the second derivative at 4. So that's 4 to the 4th, or 256. So now when I come back over to the trapezoidal error approximation, b is 4 minus a is 1, quantity cubed, over 12. I leave that as n squared. My maximum value of the second derivative on the interval for this situation is 256. And that is less than or equal to my error value that they want me to less than or equal to. So the 0.00001. And I remember when I was first doing these, I would get mixed up on what side that I needed to have. You need the error formula less than or equal to what they have as want to be less than or equal to. Now I need to solve this for n. So in solving this for n, certainly there's other things that you can simplify. Well, 4 minus 1 is 3. 3 cubed is a 27 there. So I have 27 times the 256 over the 12n squared is less than or equal to that 0.00001. And now I want to solve for my n squared. Well, n squared is a positive value. It's the number of subintervals. And so I can multiply both sides of an inequality by a positive number, and my inequality is still preserved. So I'm going to multiply both sides by n squared, but then divide both sides by the 0.00001. So I'll have 27 times 256 divided by 12 times that 0.00001 is less than or equal to n squared, and then take the square root of both sides. So n is greater than or equal to 7,589.466, but n has to be a whole number and you have to round up. Even with this being a 4, I need to round up because my n has to be a whole number, and if I go down I won't meet my requirement. So take n is equal to 7,590. So we would need to cut it up into that many places. It would be a computer program that we would want to run that through to find our approximation with trapezoidal rule with that size of an n. Now let's see what we would have for Simpson's rule. Well, Simpson's rule here is this expression. So I have my 4 minus 1 to the 5th power over 180 n to the 4th times the maximum value that the 4th derivative takes on over that interval. So I have the second derivative is x to the 4th. The third derivative is 4x to the 3rd, and the 4th derivative is 12x squared. Well, 12x squared is a parabola pointing or going up. Its vertex is at 0, 0. So when you're looking over the interval from 1 to 4, again, it's going to be positive and have its highest value at the right endpoint. Now, if it were any type of a function that would curve throughout it, you would want to apply the extreme value theorem in the side work to this to figure out what your maximum value of the absolute value of your 4th derivative is. Here, since it's always increasing positively away, our highest value for our absolute value will be at the right endpoint. So evaluating this at 4 squared is 16, and then our 12 times 16 is what we're going to have in that maximum value here. So I'll just do the 12 times my actually 4 squared. Let's just do it that way so you can see where the numbers are. And then that has to be less than or equal to my 0.00001. Now, doing the same solving process, we are going to multiply both sides by n to the 4th and divide both sides by that 0.00001. And 4 minus 1 is 3, so I have 3 to the 5th times the 12 times the 4 squared over 180 times 0.00001 is less than or equal to n to the 4th. And then we're going to take the 4th root of both sides. Our n is greater than or equal to 71.3524. But again, we need to round up. And actually for Simpson's rule, you have to round up to the next even number. Simpson's rule, your n has to be even. Now this will round up to 72, which is even, but if you had this to be like 70.04, you would have to still go up to 72. Your n has to be even for Simpson's rule. So we're going to take our n is equal to 72. Look at the difference in the number of subintervals you need to use to make the same accuracy for the same question, comparing your trapezoidal rule approximation to your Simpson's rule approximation. It's a huge difference in the number of calculations that would need to be made in order to get the same accuracy. So I hope you've found this video to be helpful. Thank you for watching my video, and be sure to hit the like button if it's something that you found to be helpful, and subscribe to my channel.